Okay, question number 9. We have a unit circle. The unit circle will have the equation y squared equals 1 minus x squared, y equals plus or minus the square root of 1 minus x squared. And since p is always going to be up here for this question, I'm going to consider only the positive square root, so the positive semicircle. And while I'm here, I'm taking the derivative. It's a chain rule happening. So it's a half. 1 minus x squared to the negative a half. Derivative of the inside is minus 2x. The 2's will cancel, leave minus x on top of the square root of 1 minus x squared. That's y dash. Okay. Show that the equation of the line that passes through point A and point B is this. Okay, so I've got to show that the gradient is equal to negative 1 on root 3 and the y-intercept is equal to 2 on root 3. Okay, so I can get the gradient two ways. The gradient's going to be minus x on top of the square root of 1 minus x squared, and that's going to equal this gradient triangle where this coordinate here is x and the square root of 1 minus x squared, and this coordinate is 2, 0. So it's going to be y2 minus y1 over x2 minus x1, which is going to be y2. So the square root of 1 minus x squared over, so minus 0, x minus 2. And if I go minus x times x minus 2 equals 1 minus x squared square root squared minus x squared plus 2x equals 1 minus x squared. 2x equals 1, x equals a half, which means the gradient equals negative a half over the square root of 1 minus a half squared, negative a half over the square root of 1 minus a quarter, the square root of 3/4, square root of 3 on 2 over negative a half times 2 on root 3, negative 1 on root 3. The gradient equals negative 1 on root 3, which is what I needed to show. And I know that y equals negative 1 on root 3 x plus c. And if I sub in the points 0 and 2, c equals 2 on root 3. Done. So that's part A done. So I now know that that point there is 2 on root 3. Okay, part B. I have this matrix. Q is the only thing that's there. Q is the dilation from the x-axis. It's the thing that multiplies the y-coordinate. Find the values of Q for which the intersection of the unit circle at least once. Okay, so when Q equals 1, it has at least once. It's got once. And when Q equals negative 1, it is also once. When Q is bigger than 1, we have a higher dilation. And when Q is smaller than negative 1, so Q's got to be in between negative 1 and 1, but it can't equal 0. So Q is an element of negative 1 to 0, union 0 to 1. Inclusive because that's when it touches. Okay, part 2. Let the graph of H intersect the circle twice. So I know my Q is between negative 1 and 1, except 0. Find the Q for which the coordinate of the point of intersection only have positive values, the coordinates of the points of intersection. Okay, so over here is no good because while my y is positive, my x is negative. Over here is no good. Down here is no good. So I'm only looking for the values in here, because the minute it dips below here, I'm going to be over here. So I want Q that goes between these 2 points. Okay, so draw another picture here. I want the line to go through there, up to the line going through there. And that's when Q equals 1. So 1 is my upper limit. And I'll include it because at that point there are 2 positive points. To get this point down here, I won't include it, which means I want the y-intercept to equal 1, and I know currently the y-intercept equals 2 on root 3. So Q times 2 on root 3 has to equal 1, therefore Q equals root 3 on 2. So root 3 on 2, non-inclusive, will be my lower value, and that will give me the intersection point there. Don't want to include it because I can't have a 0 because it's got to be positive. So that's my range because I want it to intersect in those spots. If it's bigger than 1, I'll have no intersection point. If it's smaller than this value, I will have a negative as well as a positive. Okay, and in part C, let Q be 0 to 1, let be the point of intersection. So G is the area. So I've got this right angle triangle with theta, and that hypotenuse is 1. Therefore, that's cos theta and that's sine theta. Therefore, the height of this triangle is sine of theta. Therefore, G should equal a half base, should be 2, times the height, which should be sine theta. G equals the sine of theta. Determine the maximum possible area of the vector. So G dash is the cos of theta, but the only way, what have I got here? Okay, so where P dash is always the point of intersection that is closest to A. So P dash is not there, P dash is here. Therefore, this is the highest point that P dash can be, which means that's when the tangent touches that curve. So that's sort of gradient of -1 on root 3. And if the tan of theta equals the gradient, then the tan of theta will equal root 3 since I've got a perpendicular. Therefore, theta equals pi on 3. Okay, so my theta goes from pi on 3, 0 to pi on 3. My theta could be 0, where P dash is down here. The highest it can be is pi on 3. So, determine the maximum area of the triangle. Well, my cos curve goes like, my sine curve goes like that, but I'm only going to pi on 3. Therefore, the maximum will occur when theta is pi on 3. So max occurs at the endpoint at theta equals pi on 3. Therefore, area will equal G of pi on 3, which will be the sine of pi on 3, which is root 3 on 2 square units.